Good morning, everyone. My name is Paulina Krupska-Wolas, and I work at the Laboratory of Analysis and Nondestructive Investigation of Heritage Objects of the National Museum in Kraków, Poland. I am also a PhD student at the Faculty of Physics and Applied Computer Science at the HEH University of Science. Today I am going to tell you about the use of two spectroscopic methods, which I mean SWIR reflectance imaging spectroscopy and Raman spectroscopy in a study of amber objects. The outline of the presentation is as follows. At the beginning, I will tell something about the object and references, and then I will specify spectroscopy methods used in this study. Then I will discuss the research results, among others, how amber and its imitation were identified. In the next step, I will tell you how the multivariate imaging data was processed in order to reduce number of spectra to analyze. Next, I will focus on discussing the observed amber degradation. Finally, an attempt was made to classify the altered amber against the amber references. The amber altar of the Lord's Passion from the National Museum in Kraków collection of European decorative arts was selected as a case study. The altar is attributed to the authorship of Michael Schodellock. It is dated to the middle of the 17th century. The structure and the base of the altar are wooden, the front and sides are lined with amber tiles of various shades and transparency, as well as plaques with figural scenes and ornaments carved in ivory. It should also be mentioned that only the body of the altar was examined. The amber cross was not measured. A set of reference amber samples from the collection of the Museum of the Earth of the Polish Academy of Science in Warsaw was also examined with the reflectance imaging spectroscopy technique. The collection counts in total 63 samples. Some of them are listed here on the slide. The measurement was carried out using an imaging system with short wavelength infrared reflectance spectroscopy SWIR, the spectral range from 1000 to 2500 nanometers, provided by SPECIM. The system is equipped with 6-point halogen light sources arranged symmetrically on both sides of the camera at the angle of 45 degrees. The scanning system was positioned in vertical geometry. The obtained hyperspectral images were normalized to the white, spectral and white plate and reduced with dark current. Reference and dark current measurements were taken under the same parameters for the actual object measurements. Data analysis was performed with the Python scripting language and with the NV software. Raman spectra were collected with a portable Raman spectrometer Delta Nu. Spectra were acquired using a 785 nanometer diode laser. The measurements were carried out in a distance about 1 cm, which is the value for the collection of the most intensive Raman signal. Additionally, an attempt was made to register the Raman depth profiling for figures of St. Peter and Paul to try to collect spectral information about amber surface degradation. The scans were collected from a distance of the most intensive Raman signal, called middle distance. Then the spectra were registered from the distance of about a half centimeter near and about an 1.5 centimeter called for. And now we can go straight to results section. Golok in his work shows a set of typical amber reflectance spectra and presents a method of identifying amber imitation by determining two coefficients, as is noted here on the slide. The values of the coefficients were determined for each pixel of the hyperspectral image. A map of the value of one of the coefficients is shown on the right. Values outside the range of those determined for the reference amber are marked in black. Values remaining in the range are colored. As expected, the location of the ivory plaques marked with white arrows remain black. Similar situation takes place for the wooden base of the altar, which is marked with a yellow arrow. During reflectance imaging spectroscopy measurements, the statue of the Virgin Mary, marked with a purple arrow, was wrapped with an additional layer of material to eliminate any possible damage. This is the reason for excluding the material of the figure as an amber. Therefore, the statue of the Virgin Mary was not further analyzed with reflectance imaging spectroscopy. Also, some shining areas with high reflection degree are black, marked here with blue arrows. Selected areas marked with green arrows of the amber altar also remain black. It is suspected that these are places where the losses in the plates are filled with imitation of amber. Raman spectroscopy showed the presence of epoxy resin at the selected measurement point number 5. The spectrum is shown in the middle of the slide and the bands assignments you can find above. Additionally, Raman spectra collected from selected places on the Arthur, points 1 to 4, confirmed the presence of amber in the remaining areas marked with color in the color map figure presented before and here on the right. We should still remember that reflectance imaging data consists over 1,000,000 pixels to analyze. Exactly, it is 1200 by 772 spectra, and we must somehow deal with that. Firstly, a false colors images can be analyzed. Here we can see the visible image of the object, next the false colors image. The RGB channels were chosen among the SWIR range. Next, some density reduction algorithms were used. The principal component analyzes PCA and non-negative matrix factorization NMF. Then another false colors images were completed based on the chosen components obtained in PCA and NMF analysis. The most important material property we can observe here is the specific diversity of the amber within the object. We can notice that probably two types of amber were used, and moreover, the amber place location is not random. They are located alternately. The scarce property is not completely noticeable in the visible image. So let's divide the Arthur's amber into two groups, green and red one. The even plates of the Arthur's body, Virgin Mary and St. John figures, red put on the Arthur are green, and the odd plates, St. Peter and Paul figures and left foot of the Arthur are red one. Moreover, we can observe also some regions of particular interest as the amber plate under the middle ovary plaque or aberrations of the plates on the right first two tiers. The set of reflectance representative spectra was determined using the pixel purity index (PPI) algorithm. As a result of PPI, a cluster map was obtained. Based on the PPI cluster map, the average spectra for each specified cluster were calculated. Further, the PPI cluster map image and NMF result image were compared. The representative PPI spectra have been grouped into the red and green class according to NMF results. We can notice here that the most of the even plates of the Arthur assigned to the green NMF class are described by one PPI cluster, the pink one. Only a plate mentioned before, the plate under the middle ivory plaque, also assigned to the green class, is described by a different cluster. The aberrations of two plates on the right are described by a cluster number 14. The red NMF class is more differential. It is described by 7 PPI clusters. In a further analysis, we will try to determine if the PPI cluster division can be somehow connected with a kind of the amber used. The obtained representative spectra show the greatest difference in the intensity of the 14, 15, and 1639 nanometer bands. The presence of the 14-15 nanometer band is related to the stretching vibrations of a single carbon-hydrogen bond conjugated with oxygen-hydrogen bond of water. It is suspected that the 1639 nanometer band indicates the presence of organic acids, which are characterized by the presence of combination bands and overtones of oxygen-hydrogen bond stretching vibrations, among others, in the range of 1400 to 1615 nanometers. Both the 14-15 nanometer and 1639 nanometer bands are shallower for the NMF green class than for the red one. Moreover, double the maximum absorption can be observed for 1405 and 1440 nanometers in the red class. It may be related to the decrease of water and organic acids, including succinic acid also, content in green class amber. It is also known that white amber contains more air bubble inclusions than amber of a different color. The great amount of air bubbles inside an amber stone may cause less amount of structures characteristic for amber itself, like structures which can be described by reflectance spectrum bands detailed above. According to that, it is suggested that originally NMF green class amber was milky or butter color, while the NMF red class was rather cognac or sherry color, as it is now. The difference between green and red class amber was quite visible then. In addition, depth profiling by Raman spectroscopy was performed for the features of Saints Peter and Paul. The change in the band profile in the range of about 1630 and 1415 inverse centimeters proves structural changes in the amber itself, like changes in the structure related to the hexamethylene group and changes in the methylene and methyl groups. It indicates amber degradation, which is expected to be larger on the surface than in the interior amber. Also, an attempt to classify the end-member reflectance spectra was made. The PCA was performed on 10 representative reflectance spectra of the amber altar obtained by PPI algorithm and 63 reference amber spectra. As a result of the PCA, it was possible to successfully classify most of the object amber spectra into the group of succinate reference spectra. Some of the object spectra C1, C9, C11, C16, and C20 are located among the reference spectra of Polish Baltic amber, Jantary, Kazimierz, Adamów, and also close to those from Ukraine and Germany, Bitterfeld. The spectra of C5, C14, and C17 are located close to the spectra of white succinate sample and Saxon white. In addition, the C5 spectrum is also located relatively close to the reference Gedan succinate and Glessite reference spectra. In contrast, the C2 and C8 and C18 spectra remain on the edge of the plot, close to the reference spectra of succinates, Zambia, Saxon, and white amber, as well as Gedan succinates and Glessites. The division into NMF red and green class was also be taken into account while presenting the PCA results. Assignment to the specific NMF class was marked in the PCA plot. The NMF green-amber class is indeed located close to the spectra of the reference white succinates. However, C5, describing most of the even plates of the altar, also remains in close proximity to Glessites and Gedan succinates. Most of the spectra of the NMF red-amber class are surrounded by native succinates, but some of the red class spectra, like C8, the odd plates of the first two tiers of the altar, and C18, left foot of the altar, are close to the Gedan succinates and Glessites. So let's finally move to the conclusions. The amber altar of the Lord's Passion was subjected to SWIR, reflectance imaging spectroscopy, and Raman spectroscopy in order to assess the material composition of the object. It was possible to distinguish areas of interference with the original structure of amber plates and to determine that the losses were filled with epoxy resin. The amber plates of the altar have been divided into two classes, which differ probably in water content. It may indicate that originally some of the amber plates were white and others were dark, cognac or sherry. White amber contains many inclusions of air bubbles, which cause the amount of structures characteristic for amber is lower. Due to reflectance imaging spectroscopy analysis, it is suspected that two colors of amber were used: white, milky or butter, and dark, cognac or sherry. As a result of the degradation process, the differences between the amber colors are no longer visible. The arrangement of amber of both NMF classes in the object shows that the differences between amber plates are not the results of randomness, but rather the intention of the creator. The existence of a degraded amber layer for the features of Saints Peter and Paul was also found. The representative reflectance spectra of the amber altar were classified against the reference spectra. Based on the PCA analysis, it is suspected that the amber used may be native or other from Middle Europe, succinate, and or Gedan succinate and or Glessite. Based on the above, we can also admit that Raman spectroscopy and SWIR reflectance spectroscopy are complementary techniques in amber identification and assessment of amber degradation. It should be emphasized that Raman spectroscopy as confocal technique could provide many valuable information about changes in the surface of the material in relation to its interior. What is very important, both techniques are non-invasive and non-destructive and enable in situ measurements. Really, thank you for your attention.